Another classic problem that every calculus student does, it's the cylinder filled with water that's leaking. And so the cylinder is draining. This is getting lower and lower and lower. Water's leaking out of the bottom. Classic calculus problem. Everybody in AB and BC and college Calc 1 and 2, you all do it. Okay, so leaking, verb, right there. Derivative. Verb is always derivative. If you didn't notice that, the per second is kind of a dead giveaway. It's a derivative, but it's a special kind of derivative called a rate. It says the word rate in there, and there's also a per time. So that's another dead giveaway. All right, so what is this? It's 16 watts. It's cubic inches per second, all right? Cubic inches. Volume, three-dimensional, right? So that's how fast the volume of the water is changing. So let's make a little note to ourselves. V prime is 16, but wait a minute. It's leaking. It's the first time that we've had a negative verb in all of these real-life word problems. So leaking, it's actually negative 16. The word leaking is negative. How about that for a twist? All right. So the volume is losing 16 cubic inches per second. All right. Now, what else do we know? The depth of the water is 3 inches for just one snapshot. For one instant, it will reach only 3 inches tall. The cylinder of water, not the overall cylinder, right? So we're only focusing on the cylinder of water. Okay, wait a minute. Depth, wouldn't that be like this? 3 inches, right? Depth is basically the same thing as the height of the water. Let's call it h for height, because that's actually going to end up in our formula here. So the height of the water is 3. How fast, derivative, is the depth dropping? Also derivative, verb. Depth, isn't that the h? That's the height of the water. How fast is the height of the water changing? We're looking for h prime. Always know what you're looking for, okay? Or dh dt, right? All right, so v prime, h, go find h prime, write your own formula. The volume, we have to incorporate the volume of a cylinder somewhere. Integrated 3. The volume of a cylinder is just base times height. The base is a circle pi r squared, stacked h tall. If your teacher didn't tell you that it was just base times height, they were missing out, because that's really what it is. Okay, so volume of a cylinder, V equals pi r squared h, and then you take the derivative of both sides. This is all dt, right? It's dh dt secretly, so it's all with respect to time. I don't see t anywhere. That means v gets a v prime, r gets an r prime, h gets an h prime. Everything is implicit, right? But wait a minute, is there a shortcut here? Because I've got a variable times a variable, and so I'm going to have to do ho-d hi plus hi-d ho with this r squared and this h right here. Do we really want to do that? I mean, you could, it works, but isn't there something that would save us some time? What did Mr. Wade say in an earlier lesson, right? About the sliding ladder and about the rocket, the space shuttle blasting off. If anything is permanent, plug it in now to save time. If anything is changing, you have to plug it in later. What about the height? Is the height of the water staying the same? Nope, it's changing. It's always changing. What about the volume of the water? Is that changing? Yes, that's changing. What about the radius? The radius of the water is going to stay 2 all the way down. That's the magic of a cylinder. It maintains the same radius, okay? So right now, I'm going to go ahead and plug in radius 2 for the r, because the radius of the water will not change. Now the other backup plan was to do this. Once you got to the derivative with the product rule, which is a real pain here, you eventually could have established the fact that the radius is changing at 0, just like the sliding ladder's height was changing at 0. So the r prime equals 0 doesn't concern us. We just go up here, maybe clean it up a little before you take a derivative. So 2 squared is 4. Let's put that in front of the pi as a coefficient. And you're ready to go. All right. Derivative of v is implicit. It's v prime. 4 pi stays. And the derivative of h is h prime. It's just that simple. Real life, water tower, real life oil leaking out of some kind of tank, right? Could be like the cylinders that are actually inside your car that make your car run. So all this real life stuff. It's actually pretty simple, right? So v prime, what's v prime? Given negative 16, all right, equals 4 pi. H prime I don't know, isn't that what I'm trying to find? Divide both sides by 4 pi. H prime equals negative 16 over 4 pi, which will reduce to be negative 4 over pi. There we go. Why is H prime negative? Because the height of the water is dropping. Of course, it's decreasing, right? So of course it should be negative. But negative 4 over pi what's, right? Well, isn't height one-dimensional? It's just a string. It has a height, but it has no thickness. So one-dimensional, so we're talking not cubic inches, not square inches, which would be the surface area, but just inches. But it's a prime, so it's per second. And of course, an engineer could do negative 4 divided by pi button and get a more accurate decimal. We just leave it like that and walk away. All right, we did it. Okay, every calculus student must do the draining cylinder. Every calculus student must do the draining cone as well. It's a little trickier than the cylinder, not much. I'll have to do a little integrated 2 refresher with you first. But we'll get that along the way. You got a snow cone. You go to the fair, right? And you have these nice, delicious snow cones, and they're so tasty. I love those things. And then all the ice melts because it's hot, and then all of a sudden you got a bunch of liquid, and it starts leaking out of the bottom of the cone, right? It happens. All right, so it's leaking at a rate of 0.5 cubic inches per second, all right? Leaking, verb, derivative. If you didn't catch that, rate, definitely derivative. So this is obviously some kind of prime. What kind of prime is it? You've got a radius, you've got a height, you've got a volume. Well, it's cubic inches, which is 3-dimensional, so clearly it's volume, right? So 3-dimensional, volume, per second or rate, derivative, also dv dt because it's a rate and it's per second, and leaking, a negative verb, so technically negative 0.5. Okay, so that's how you throw in the negative, and you also identify the fact that it is v prime or dv dt and nothing else. All right, what else do we know here? Oh, when the depth reaches 6 inches. Okay, so when this depth of all the leftover melted delicious juice that they put in your snow cone, when it gets down to 6, okay, isn't that a height of the little cone of water? So the height is 6 inches, okay? So we've got 2 clues right there. Okay, how fast is the depth dropping? Let's see, the depth is going to be the height, but dropping, so prime. Also, how fast? Prime, okay? Hopefully you're getting really fluent in English to calculus, calculus to English, right? Looking for the keywords. How fast, derivative. Go find h prime. So h prime equals question mark. That's our question mark. All right, let's see if we can put it all together. First of all, integrated 3. The volume of a cone is 1/3 of a cylinder. And what was the cylinder? Pi r squared h. I hate this darn mark on the board right here. All right, so 1/3 pi r squared h that is not subtraction, is the volume of a cone. Archimedes, another breakthrough by Archimedes. He discovered that 3 cones fit into a cylinder exactly. You'd have to mold them out of clay and kind of push them around and warp them a little bit. You couldn't keep them perfectly as a cone, but they actually make up. He was very proud of that discovery, by the way. It was quite fascinating that he figured it out. He says that's one of his favorite discoveries, actually. I talked to him the other day. No, he said, allegedly, according to history, that it was one of his favorite discoveries. All right, now, we got that. Now, remember how to make this easier? Do you really want to do a product rule? You could, but I'd rather not. Okay, gem. If something is permanent, you can plug it in now. If something is changing, you have to wait. Wasn't the radius of the cylinder permanent all the way down? But it doesn't happen in the cone, does it? Okay, when it's completely filled with liquid, the radius of the liquid would be 3 inches, but it's going to diminish as it drops down smaller and smaller. So the radius is changing, the height's changing, the volume's changing, everything's changing. All right, well, I was hoping we could plug that in, but wait. If you say to yourself, nothing is permanent, which is true, and you take the derivative of this with a product rule, you're still going to hit a big dead end. You're going to say, why are there all these unknowns that I don't know, right? I got V's, R's, H's, V primes, R primes, H primes, and I only know 2 of them. You're going to get stuck unless you get the integrated 2 breakthrough, all right? Most of this stuff is integrated 3 in pre-calculus, occasionally pre-calculus, really, quite honestly. Most of it's integrated 3, occasionally it's integrated 2. From the side view, the flat 2-dimensional view of a 3D cone is just a triangle, okay? In the beginning, the radius is 3 and the height is 10. Now, as the liquid drains, you get smaller and smaller triangles of liquid. But I want you to think about this. This is something from integrated 2 that I taught when I taught integrated 2 called similar triangles. All right? Similar triangles, not congruent triangles, which are identical. Similar triangles are where you have the same ratio. Oh, you're only 50% as big as you used to be. You're only 30% of what you used to be. You're only 22% of what you used to be. Every triangle of snow cone liquid is similar to the larger one. For instance, eventually, wouldn't the radius get down to half of this? So we started at 3. Eventually, the radius would get down to 1.5. And at that exact moment, the height 10 would be down to height 5. You see, they go down together. So when you get half of the radius, you get half of the height. They are always the same ratio together. That is similar triangles from integrated 2. And if you had an iffy integrated 2 teacher, well, let me show you the real deal then right here. Okay. Radius goes to height as 3 goes to 10. It will keep a 3/10 relationship all the way down. 1.5 out of 5 is also 3/10. Okay? Every time this thing diminishes, the radius and height have this relationship right here. And that's called similar triangles. That might be brand new if you never got to see that in integrated 2. Okay? This is the only breakthrough that solves the cone problem. That's why it's a tricky problem. Okay, so if R over H equals 3/10, 3 over 10, you could multiply the H up to the other side, and you could say R equals 3/10 H. The radius shall be 3/10 of the height at all times. That's true, all right? Also, though, you could get the H by itself. Now, see, here's the question I'm going to ask you. Would you rather get H by itself or R by itself, all right? It's okay to get R by itself. We could just square 3/10 H when we plug it in here, okay? Because this relationship is permanent all the way down, so we could plug it in now. See that? All right. Also, you could cross multiply, and you could do like 10R and 3H, and then try to get the H by itself. I mean, it's whatever you want to do, okay? Now, I wouldn't be too scared that you have to take the 3/10 H, and you've got to square it right here. I wouldn't let that scare me off and try to get H by itself instead, because here's the deal. Here's why this is going to be easier. If you change R's into H's and you get all H's into the problem, isn't the hint directly related to H, right? So we probably should be going to H world and not R world, all right? If you had cross multiplied and gotten 10R equals 3H, and then divided both sides by 3 to get H alone, is H equal to 10R over 3? Sure, yeah. I mean, that's true. It's just kind of the opposite of this, but it means the same thing. So could you replace H with 10R over 3? Sure, but you're going to convert the whole problem to R world, all right? You don't have any hints about the radius. Now, there's a way to do it that way, but it's going to cost you like 5 extra steps, so why would you do it? So here's where I want you to use some of your calculus and your mathematical instincts and say, if my hint contains H, I really want to try to write things in terms of H. If my hint contains radius, Maybe I'll give you r equals 2 on the sample test or the test. Then I want to convert to all r's, so it just depends. Be flexible, okay? All right, so hopefully you understand the similar triangles thing because you either never learned it or you haven't seen it in a long time. So volume equals 1/3 pi, change r into 3/10 height, quantity squared, times h. If you don't do that step of similar triangles, you will never solve this problem. It is the only way, BC students. All right, now we're going to clean this up before we take the derivative. 1/3 pi square 3, 9. Square 10, 100. Square h squared, times an extra h cubed. Okay? Volume should always be three-dimensional, so you have to have a power of 3 on your variables in there anyway. By the way, not many teachers show you this. R squared h to the first. 2 plus 1 is 3, because you add powers. That is 3 dimensions. That does count, okay? If anybody's never shown you that before. All right, oh, we can cross cancel. 3 and 9, let's put a 3 up here. And I believe we've gotten as far as we can go in the volume. We just need to get to volume prime to incorporate this hint right here. All right, let's try it. Let's put it back on this other board over here. Ta-da! All right, let's finish off today. V prime, or dV/dt, equals coefficient stays. Derivative of h cubed. 3 comes down, h squared, chain rule of h prime. Everybody gets a prime. Unless you see a t in there, which occasionally you will, not very often. Okay? So everybody's implicit. No cross cancellation. So let's just call that 3 times 3 is 9 pi over 100. I'll just consolidate it to one fraction. How about that? H squared h prime v prime. Plug in the hints, you're done. What's v prime? Negative 0.5. Ooh, don't like decimals. Let's plug in negative 1/2. Okay? 9 pi over 100. Do we know h or h prime? H is 6. Bingo. 6 squared, 36. Oh, we can get h prime by itself. Piece of cake. This is back to middle school now, right? 36 and 100. Let's see about the cross cancellation. They're both even, so 2 goes into both. 4 goes into both. 6 goes into 36, but not 100. Okay, 4 is your best bet. 4 times 25 makes 100. 4 quarters makes $1. 4 times 9 is 36. And you get negative 1/2 equals 9 times 9 is 81 pi out of 25, h prime. Get h prime by itself, multiply both sides by the reciprocal. I've been training you how to do that for 3 years. H prime equals negative 1/2 times the reciprocal 25 over 81 pi. 2 and 25 don't cross cancel, too bad. So negative 25 over double 81 is 162 pi. As far as you can go. Units. H, height of the snow cone melt. Height is one-dimensional, so that is inches. Prime is per second. You're done. There you go. It's a bonus lesson. Click the link and you can find out how Mr. Wade used related rates from calculus to solve a real-life problem in my own backyard. Click it.